Hey, good morning, everyone. Let's get started for today's class. So
Good
today's
morning, sir.
topic, yeah, good morning. And today's lecture will be on multistage amplifiers and differential amplifiers. But before we get started, I just want to complete the discussion on MOSFETs. I'm yet to talk about the capacitances inside a MOSFET, and I'll briefly talk about them, and then we will move on to multistage amplifiers and differential amplifiers. There is one more topic, which is power amplifiers, which I'll try to cover if possible in a class. If not, I will just post a video. I hope you were able to look at the lecture which I posted yesterday. So please do go through it. I'm doing that purely because we are running out of time, and I want to basically touch upon the topics that are there, at least to give you a basic idea. Okay. All right. So just a short discussion on capacitances in a MOSFET. Okay. So we have looked at the capacitors in BJT, and we have also tried to look at the pole location and so on. Similarly, if you look at a MOSFET, right, let's start with the structure of a MOSFET, right? You can basically guess some of the capacitances that will be present. Okay. Now, first of all, this is a metal oxide and a semiconductor. You basically have some channel like this, and if you are basically operating this in the saturation region, your channel is going to look something like this, right? So here the channel is basically a conductive type of, it's a conductive thing, right? So you have a metal, you have an oxide, and then you have the semiconductor, which is basically no conduction, right? So obviously you have a parallel plate capacitor, right? So you have some capacitance which you can say exists between the gate and the channel. Okay. And in order to now, where is the channel connected? On one side it is connected to the source, and on the other side it is connected to the drain, because anyway, in the saturation region also, this particular region is a depletion region, and so the charge carriers get swept across the barrier, right? So part of the capacitance is split into the gate, between the gate and the source. So if we draw the equivalent, the symbol of the MOSFET, we can say that there is going to be a capacitor existing between the gate and the source, which is called a CGS, and another part of the capacitor is split between, it is between the gate and the drain, which is called a CGD. Okay. The origin of the capacitor is that it is a normal parallel plate capacitor, and in fact CGS and CGD are both parallel to are both proportional to the area which is given by the product of the width and the length. Okay. Now, where else can we have capacitors? So here, if you see, this is a N plus region with a P minus substrate. This is also an N plus region. So we have already looked at it, that we have two diodes which are sitting like this, right? And we have also discussed about this, that these two diodes need to be in reverse bias. Let me call it D1 and D2. D1 and D2 are reverse biased, and therefore they will have their depletion region, and because of that they will have the depletion capacitance, right? Any diode will have a capacitor, and this the depletion region capacitance is also a function of the voltage applied across it. So in other words, this capacitor is a function of the voltage between the, let's say this is our bulk terminal. Okay. So this capacitor, which is formed between, let's say, the source and the bulk, let me just put it like this, right? This is the bulk terminal. Okay. So this capacitor, which is formed between the source and the bulk, is called CSB. Okay. This is a non-linear capacitor. Why do we call it as a non-linear capacitor? Because it is a function of the voltage between the source and the bulk. Basically, it is a function of the source bulk voltage. Same way, you also have the capacitor CDB, right? This is also a nonlinear capacitance. In other words, it's a capacitance which varies as a function of the drain to bulk voltage. Okay. Now, if bulk is connected, bulk and source are connected together or tied together, right? Then VBS is 0 and TSB is not in the picture. Anyway, both are connected, so shorted together. So CSB is not considered. Okay. Whereas all the other capacitors are coming into the picture. Okay. So the small signal equivalent circuit becomes very similar to what we did for BJTs, right? Now we have CGS connecting like this, and you have GM VGS, right? VGS defined as across this, right? And then you have R0, and then you will have CDB. So this is for the circuit where you have connected the bulk and the source together. Okay. So now this is the gate terminal, this is the drain terminal, this is the source terminal, right? Let's assume that you have connected both together. So this is your CDB, and your CGD is like this. Now this is a circuit that we have already seen, a similar type of circuit we have already seen in the case of BJT, right? So we know how to use Miller's approximation in order to solve for the frequency response. Okay. Right? And because of all these capacitors, you will basically have so many number of poles sitting in the circuit. Okay. So using Miller approximation, you can say that you have two capacitors in the. If you take a common source amplifier, you'll have two poles. One will be the dominant pole, and the other will be the non-dominant pole. Okay. So the same analysis, the same kind of discussion we had for BJTs holds good for this as well. All right. Okay. Any doubts? Any questions?
So okay. Why did we ground that CBS capacitor?
Why did we ground it? So here, ground as in like I have tied the bulk and the source together here. This is a source node. Right. Of course, if you want to draw a common source amplifier, then obviously the source gets grounded. But if you connect the bulk and the source together, then whatever I have drawn, holds good. Is it okay?
Okay, sir. Thank you.
Yeah. All right. Okay, so let's start off with the next topic, which is basically multi-stage amplifiers. Now, I am not going to go very deep into all the types, but typically when you look at any analog circuit, okay, so if you look at the internal circuit of a op-amp, you will see that there are multiple stages of amplification. So all the gain that you require cannot be got from a single stage, because a single stage gain will be, as you would have experienced in the lab exercises, single stage gain will be around 20, 30, 40, something like that. Okay, because you can do certain other techniques to improve the gain. That's another thing, but then still you can't get all the gain that you want out of a single stage. So typically what is done is that you can put multiple stages of amplification in cascade. Okay. So what happens, let's say this is amplifier 1, this is amplifier 2, this is amplifier, let's say N. Okay. So let's call this as V out 1, V out 2, let's say V out N. If you are giving a certain V in, right, then V out 1 is what? It is A1 times V in. And what is V out 2? The input of the amplifier 2 is A times V in, right? So it becomes A2 times A1 times V in, right? So basically A1, A2 times V in. And therefore, V out N by extension can be written as what? A1, A2, all the way down to AN times V in. Okay. Now, if you take the overall gain, what is the overall gain? It is the product of A1, A2, A3 all the way up to A. So if you take it in the log scale, which is what many times we do, right? So you say, okay, this amplifier has a gain of, let's say, 10 dB, the other amplifier has a gain of 15 dB. So what happens? The overall gain can be taken as the summation of, let's say, I1 to N, A, I in dB. Okay. And typically we take the A I of dB scale is taken as 20 times the logarithm of A I. So in the log scale, you basically add the thing. So whenever you deal with uh, multi-stage amplifiers, basically what you do is you usually deal in terms of logarithmic scales, and then you say, okay, this is a 10 dB amplifier, another 15 dB amplifier, another 20 dB amplifier. Just put three in cascade. So this is what is called as cascading. Okay, you add up the gains. All right. Now let's just look a little closer at a more abstract level. Let's say this is A1 and let's say this is A2. Let's just look at the interface of these two amplifiers. Okay. Many times, many people have issues when it comes to the interface. Okay. That's where all problems begin. Okay. So A1 by itself might work very well and A2 by itself will work very well, but when you put both together, that's when all the fun happens. Now, it is very important to understand that you need to know what is the input impedance of A2. Okay. So when you are designing A1, right, you should be able to know what will be the gain when you, let's say you're designing two amplifiers, you're putting both of them in cascade, and you want an overall gain of, let's say, some 50 dB or 60 dB. Okay. 60 dB gain is a gain of 1000, right? So suppose you want to put two amplifiers in cascade. Now if you design A1 in complete isolation with and A2 also totally isolated from each other, when you put both together, even if their product of the two intrinsic gains are going to be 1000, when you put both together, you will not get a gain of 1000. That is because of the impact of the load impedance and the input impedance presented by the other stage. Okay. So when you are designing A1, you have to design it in such a way that A1 is able to drive a load impedance. RL1 now becomes R in 2. Okay. And for the this also can be, this is the way that you drive. Okay. On the other hand, when you are designing A2, you should be able to understand it as some Bs with a source resistance Rs, which is equal to the output impedance of 1, which is coming into A2, right? So basically, you need to take into account what happens, when you put two amplifiers together, their input and output impedances will play a role. Okay. So let's say Vs can be taken as the intrinsic gain A1 times Vin, okay, and Rs will be the R of 1, okay, and so when you put it together in a system, when the second amplifier comes, this input impedance R in 2 will come into the picture. Okay. So there will be an impedance division between R of 1 and R in 2. So for a good amplifier, you have R of 1 being very low and R in 2 being very high. Okay. If that is the case, then the product of the intrinsic gains will be the total gain. Otherwise, these factors will basically come into the picture. Okay. So the other place where things change is that if A1 can be, instead of just looking at the DC gain, let's throw in their pole frequency. Let's consider both of them to be single pole amplifiers, right? So let's say, although they might have multiple poles, okay, usually the response is dominated by the lowest pole, okay, typically amplifiers are designed such that the lowest pole dominates the entire response, and therefore it more or less behaves as a single pole system. Okay. In other words, your first pole may be here and your second pole may be here. So let's say this is omega p1 and this is omega p2. For most part of the response, this is what is called as the dominant pole, and this dominates the response of the amplifier. Okay. So you can, for pretty much, you can kind of approximate this amplifier as a single pole amplifier. Okay. So let's say this is 1 by S by omega p1, and A2 is given by A20 or A2 naught plus 1 divided by 1 plus S by omega p2. Okay. Now when you put these two, what does it mean? The 3 dB frequency or the 3 dB bandwidth of this amplifier is omega p1, and the 3 dB bandwidth of this second amplifier is omega p2. Now when you put both amplifiers together, what happens to the bandwidth? What is the bandwidth of this composite system A? Okay. So let us, exactly, it will decrease. Have you gone through this thing? Like, have you written the equation equated to? Have you done it in any other? Maybe in Dr. Anoop's class?
Sir, no, sir.
No. Okay. Okay. Then let me. Yeah, you're right. So it will basically decrease. Okay. So then A of S can be written as what? A10 A2 naught divided by 1 plus S by omega P1 into 1 plus S by omega P2. Right. So now you have a two-pole system, right? And the frequency response of this is going to be different. Okay. Now again, just as a side note, you can see that now if you expand the denominator, you will basically get a S squared term and a S term and a constant term. Okay. So if you give a step to this amplifier, right, as an amplifier which has got two poles, basically depending on whether the denominator tells you, depending on whether it's an underdamped system or an overdamped system or a critically damped system, your settling response will be accordingly like that. Okay. So this is a clear case of where you have a second order system even without having a single inductor. Okay. So just as a side note. So one thing we can do is, let's assume A1 equal to A2, just for us to get an understanding of how things are. Okay, which basically means that omega P1 is equal to omega P2 and A10 is A20. Then what happens? Let's say these two is equal to some A naught. Okay, so what happens to A of S? A of S can be written as A naught squared divided by 1 plus S by omega P. Let's say this is also equal to omega P, the whole square. Okay. Now we are interested in finding the 3 dB bandwidth of this of A of S. Basically the cascaded amplifier, we are interested in finding out the 3 dB bandwidth of this system. Okay. Now this can also be extended. Let's say B of S is, I'm just going to say there are n stages, so it becomes A naught to the power of n into 1 by S by omega P to the power of n. Okay. Now if we are interested in finding out this one, what is the 3 dB bandwidth? By definition, that is the place where it becomes, the gain becomes 1 by root 2. Right? So magnitude of A of S becomes A naught squared, the overall gain, divided by 2 at omega 3 dB. Right? So let us equate that. So you find, let us say A of j omega. Okay. So what I will do is, for the sake of convenience, since all of you are fairly well versed with mathematical things, let me derive it for the general case. Okay. For, let's say, B of S. Okay. So then it becomes easier. Okay. Or in other words, basically base, it means that B of S magnitude becomes A naught to the power of n divided by root 2 at omega 3 dB. So after this, I'll just do it with B of S. Okay. Now, what is B of j omega? B of j omega is a naught to the power of n divided by n j omega 3 dB, or let me just say j omega divided by omega p to the whole power n. Right. Now, what is magnitude of B of j omega? Magnitude of B of j omega is nothing but a naught to the power of n divided by root of 1 plus omega by omega p, right, the whole square to the whole power n, correct? So if you had n equal to 1, it was root of 1 plus omega by omega p the whole square. Now you have n such terms in the denominator, so this is the expression. So we want at B of j omega p, magnitude becomes a naught to the power of n by root 2 is equal to a naught to the power of n divided by root of 1 plus omega by omega p the whole square, the whole power n. So what happens? Root 2 is equal to root of 1 plus omega by omega p the whole square to the power of n. Now squaring on both sides, what do you get? 2 is 2 to the power of 1 by squaring on both sides and taking the nth root, you basically get 2 to the power of 1 by n is equal to 1 by omega, let me write it as 3 dB, omega 3 dB by omega p, the whole square, right? So omega 3 dB can be written as what? 2 to the power of 1 by n minus 1 into omega p root of this. Okay. Okay. So in other words, what are we saying here? Okay, let me just write this expression here. Omega 3 dB is equal to omega p root of 2 to the power of 1 by n minus 1. Right? So for n equal to 2, f3 dB can be taken as what? The pole frequency into, so this becomes root of 2, 1.414 minus 1 is 0.414, right? So basically it is a fraction of Fp becomes what? Root of 0.414, that is 0.643 times Fp. Okay. So whatever you predicted earlier is absolutely right. So for a two-stage system, or for that matter any multi-stage system, the bandwidth is definitely lesser than f3 dB is always lesser than the single pole 3 dB frequency of the individual amplifiers. Yeah, someone has any question? I can hear that one of your mics is unmuted. Okay. So always if you take multiple stages of an amplifier in cascade, right, the effective 3 dB bandwidth is definitely going to be lesser than the individual 3 dB bandwidth of your system. Okay. Now we have taken the assumption that all the amplifiers are the same. Now if that is not the case, for a generic system we can say that the way you calculate it is that a1 times a2 times an divided by 1 by 1 plus s by omega p1, 1 plus s by omega p2 multiplied by 1 plus s by omega pn, right, is equal to a1 a2 all the way down to an divided by root 2, right? I mean the magnitude. So basically you take so this is the, let me say, this is the overall a of s. Okay, and what do you do for finding out the 3 dB bandwidth? It basically becomes root 2 is equal to 1 plus omega by omega p1 the whole square, right? Let's take out the root into 1 plus omega by omega p2 the whole square into 1 plus omega by omega p n the whole square. You equate this, and these are the omega 3 dB, omega 3 dB, omega 3 dB. You solve this and you will basically get the expression for the 3 dB frequency of your entire cascade. Okay, so this is our discussion at a more system level. Okay, now the other thing that I want to talk about is basically we have already looked at one instance of our cascaded amplifiers, right? You have already looked at the common emitter with common collector configuration, right? So I think you have already done this in the lab as well, right? We saw the necessity for this. This is basically if you want to drive a load impedance which is low, you basically have this providing the gain and this providing the drive. Okay, and you've already done this in lab. Now another way configuration can also be a CE with a CB. Okay, so a common emitter with a common base. Okay, the equivalent thing in MOSFET would be basically a common source with a common drain. Okay, basically the same thing works. It's the same thing. Here again, the equivalent would be a common source with a common gate. So now let's just take a look at CE with the CB. All right. So what happens here? Let's say this is your common source amplifier, right? You take this and you give it as an input to a common base amplifier, and you take an output. Okay. Now this, if you kind of draw it more neatly, will look something like this. Right? This is V in. This is some bias voltage. This is your V out. Okay. What does it mean? Basically, you are stacking two transistors, right? And this configuration is what is called as a cascode. Okay, this is not cascade; it's called cascode. Okay, this is a cascode amplifier, and the same thing can be done with MOSFETs also. Okay, you give some bias voltage, and this becomes your V in, your V out. Many times for cascode amplifiers, you do not use a resistive load; you will instead use a current source load. Okay. Now, because a current source load will provide you with better output impedance and so on. Okay. Now, this is what is called as cascoding, and cascode amplifiers are used, especially in probably not so widely in MOSFETs, but they are quite widely used in, not so widely in BJTs, but they are definitely very widely used in MOSFETs, especially in more advanced process technology nodes. Of course, we will go deeper into it at in the analog VLSI course, which I offer as elective. So basically, I'll just give you qualitatively. Qualitatively, what happens is the output impedance seen down, R out, is very high. Okay, and therefore this is used to provide higher gain. Okay, so let me just stop with this because we don't have the time or to go through these things in a very detailed way. But when you can stack two transistors like this, and that is called as a cascode amplifier. Okay, okay. Now a lot of the advantages that you get by cascoding is lost when you put a resistor, which is why you put a current source load. And but anyway, we will not go deeper into these things. All right. Now the other thing is, yeah. Okay, so before that I have to cover differential amplifiers. Okay, so let us move to the next topic, which is basically differential amplifiers. Now I think you have already studied the advantages of having differences. So what is a differential signal? You have a common mode. So for example, a single-ended signal will be like this, right? V in is given as some VDC plus some VAC. Let's say this is A sine omega t. So which basically means you have some sinusoidal signal and the reference is always it is referred to ground. What is the differential signal? I think you have done it in the other part of the analog electronics course, right? What is the different signal?
Basically, a difference between two single-ended signals. Like,
Correct. So the same signal can be expressed as, let's say, a Vin plus and a Vin minus, right? And it can be, let's say, both of them have the same DC component, and this will be A by 2 sine omega t, and this will be minus A by 2 sine omega t, right? So in other words, you can say that, if this is the DC level, right? Let's say Vn plus is going to look like this. Let's say this is V in P, and what is V in M? V in M or the V in minus is going to look like this. Basically, the amplitude is A by 2, right? So differential signals can be understood as being equal in amplitude and opposite in phase. Correct? So, and now the reference is not with respect to ground, it is with respect to each other. So the effective V in can be written as what? V in P minus V in M. Okay. If you subtract the two, what you will get? You will basically get A sine omega t again. Okay. So the advantage of, so this is what we call as differential signals. Okay. The same signal V in, right? Of course, forget about the DC component, right? The AC component is expressed as two signals which are equal in amplitude, but they are just basically opposite in phase or 180 degrees out of phase. And the effective differential signal is defined as the difference between the two signals. Okay. Now, why do we go for differential signals? What is the advantage? Okay. So let us say you have a signal wire. Okay. For example, let's say an audio line. Okay. Let's say it is running a very long distance. Now, some signal, this is your wire. Okay. Now, what happens? Let's say this is your signal wire. Somewhere around this line, you have, let's say, some your 50 hertz power supply line crossing. Okay. Let's say this is 50 hertz power supply line. Okay. And then you have some other, interfering, some other very, shall I say, very large signal line. Maybe another example can be what? Of course, power lines are the main culprits. Let's say some other, maybe some digital signal line which is running like this. Okay. Now, what will happen if it is a single-ended signal, right? You will have, let's say, your signal was something like this. Let's say your signal was a sinusoid. Okay. Now, what will happen to your signal? On top of this, you might have some.
Noise.
Let's say this is your 50 hertz signal riding on top of it. Okay. All right. So I mean, you can either think of it like this, or basically some noise will be there. Okay. So in other words, you can basically say the V input, or at this point, let's say this is your VA. Let's say a VA was a pure sinusoid, A sine omega t, but then let's say this is VB. By the time it reaches to VB, now there is, depending on the input impedance seen at the point B and so on, you will basically have A sine omega t plus, let's say, N of t, which is nothing but the noise from, instead of saying just noise, I'll just say interference interference noise from other sources. Okay, so in most analog systems, the biggest interferer is your 50 hertz power line. Okay, in fact, that's why when you look at any biomedical circuit, even for your project or for your circuit explanation, if you are looking at some ECG front end or EEG front end or any biomedical signal front ends, analog front ends, you will always see that there will be a 50 hertz notch. Okay, that is because the 50 hertz power line is extremely powerful, right? It's a 230 volt RMS signal. Okay, so your amplitude will be 230 times root 2. Okay, that will be the amplitude of your signal. So that it's a very large signal, and if you have I mean, in fact, for that matter, like if you have these tiny biopotential electrodes, right, they will capture some of that interference in their signals. Okay, and you will see that 50 hertz riding on top of it very easily. Okay, so in order to remove that 50 hertz thing, you will put a notch filter at 50 hertz. Okay, to remove the power supply component and then amplify the thing. And it's especially done in biomedical signals because the bandwidth of the biomedical signals is very low. If you look at ECG signals, it would be like, I think, what, less than 30 hertz, something like that. Even EEG is like, very low, right? So that is the reason why they, and 50 hertz is a big interferer. Okay. In audio, because that's at the lower end, people try to remove it and so on, but probably they don't put a notch filter per se, because that also falls in your audio range. Okay, so that is what happens. Okay, whatever it is, so you basically have this interference, right? Now if you give this to any amplifier, both your N of T and your signal both are getting amplified. Okay, so there is no way to basically clear out this interference, and many times you may not even know how to get, may not even know what is the interference that is coming in. Okay, sometimes you might have noticed that if you have some sound system, public address system or some mic with some this thing, right? Like if you, some of the systems, if you bring your mobile phone near that, you'll hear that beep beep sound coming from your speakers, right? That is because of the interference caused by your mobile phone on the audio line. Okay, some mixing, something happens, and then some low frequency component gets added to your audio signal, and that becomes a big interferer. Okay, so how to solve this problem? Okay, in fact, I think it was BBC which came up with this technique. Okay, where they were running a lot of audio lines around their studio. So they said, why don't we run our signal itself as a two lines, okay, as a differential signal line. So now instead of having just one signal line, okay, what I'm going to do is I'll say this is signal P. Let me just maybe use another color. Okay. Let's say this is signal P, and I'll run a signal M. Okay, and both are going to run together. Now what happens? Let's say V in P has, or let me just say VB plus has got what? A sin omega t plus n of t, and VBN, okay, has got, okay, this is plus A by 2 sin omega t. This is minus A by 2 sin omega t plus the same interference, because both are running together, right? They have the same interference comes to both the lines of the signal, statistically speaking at least. Now if you take VB equal to VBP minus VBM, the plus minus minus, what happens? The common interference gets eliminated and you recover back your signal A sin omega t. Okay. And in order to make sure that both the plus and the minus lines are getting the same amount of interference, people thought, okay, the best way to do it is to basically twist the wires. Okay, you take two wires, twist them together, and then run it, and that is how you get the concept of twisted pair. Okay. and this became a huge success, because otherwise what they were doing is like you had to take a wire and then you have to put a lot of shielding around it. The moment you start putting shielding, the wires become bulky, the wires become more expensive because you have to put a shielding around the whole thing, right? And that is, takes a lot of cost. And finally, these people figured out, even get rid of all the shielding, just take two wires, twist them together, send differential signals all around the place. Whatever interference comes, let it come. And you put a differential amplifier and get rid of the thing. You have already studied about op amps and differential amplifiers using op amps and so on, where the common mode noise. This is what is typically called as the common mode noise. Right? This gets eliminated. Okay. So you have already studied differential amplifiers from the perspective of, by using op amps. I think you have studied instrumentation amplifiers and so on. So I'm not going into all of them. I'm only going to talk about how do you design a differential amplifier using either BJTs or MOSFETs. Okay. So I think I did see in the notes that Dr. Anup had already talked about, something like this. So what you do is you basically, let's say there is a source, let's call it as I tail. Okay, it's called as the tail current source because it's at the bottom. And let's just take the case of a perfectly matched pair of transistors. Let's say this is your Vin plus, this is your Vin minus. Okay, this becomes your Vout 1 and Vout 2. Let's say both the R's are the same. Both the transistors are, for the time being, considered to be exactly matched. Then what happens when you at DC? Okay, first let's analyze it at DC. That is to, the at DC implying that VAC is 0. Okay. Then what happens? V in P and V in minus are basically equal to some common mode DC voltage. Okay. Let's call it as V capital CM, which is the common mode DC voltage, right? This common mode DC voltage, both are the same, and therefore the current through both the branches are going to be equal. So if there is a current source of, let's say, I tail or I naught flowing here, what you have is I tail by 2 and I tail by 2. And Vout 1 is equal to Vout 2 is equal to what? VCC minus I tail by 2 into R. This is your output DC point. Okay. So basically, when you don't have any differential signals, when you don't have any AC signals, all you have is basically the equal amounts of current flowing through both the arms of the differential pair. Okay. And the other thing is that here, yeah. Now what happens when a small differential signal is applied? Okay. So let's say V in P now becomes VCM plus a delta V, and here it becomes minus a delta V. Okay. So equal at magnitude and opposite in phase. So for example, let's say your VCM is 1.5 volt, and you are adding 1 millivolt on one side and subtracting 1 millivolt on the other side. Now what will happen to the current I1 here? First of all, this node, what will happen, because these are equal and opposite, this node P does not change. Right? So this can be considered as, this is what is called as a virtual ground. Like this node does not react to differential signals. Okay. So what happens to the current through the left arm? I1, let's say this is I1. I1 can be written as I tail by 2 plus GM times delta I. And what about I2? I2 can be written as I tail by 2 minus GM times delta V. Okay. So the sum of the two currents remain the same. It remains to be I tail, right? One side has slightly more current and the other side has little lesser current. Okay, in other words, it's like you can think of it as if the current is circulating. Okay, one side has more, the other side is less, and the sum of the two becomes equal. Now what you can say is, what is V out 1? Let's say delta V out 1. V out 1 equal to V out 2 is equal to VCC minus I tail by 2 into R. Now what is the change that you can expect in V out 1? Because there is more current being pulled, it becomes minus GM times delta V times R. And what is delta V out 2? Lesser current is pulled, and therefore V out 2 will become higher. So it becomes plus GM delta V times R. Okay. So effectively, the delta V out can be written as what? 2 times GM delta V R, and the gain can be written as what? 2 times GM delta V R divided by 2 delta V, because that is the input signal, right? Plus delta V minus delta V. So the effective input signal is 2 delta V. This becomes GM R. Okay. So here what I have done is delta V out, I have defined it as V out 2 minus V out 1. Okay. Because if you take the opposite polarity, you'll get a negative gain. So basically, if you look at it, you'll be surprised to find that the gain value is the same as common emitter amplifier, right? The gain is the same as a common emitter amplifier. Now, what happens if there is a common mode signal? Let's say you add plus delta VCM plus delta VCM, that is a common mode disturbance, equal in amplitude and in the same direction. Okay, same in phase. Now what will happen? Both of them will try to increase by the same amount. Okay, so what will happen is, in principle, this will also have some, let's call it as R tail, the output impedance, right? So when both sides increase by a delta VCM, right, the node P will also slightly go up. Okay, but both sides V out 1 and V out 2 will increase by a similar factor, and therefore if you take the difference between the two signals, okay, the common mode noise will get obviously rejected. Okay, so this is the way differential amplifiers work, and the continuation of this probably so tomorrow's class will be taken by Dr. Anup. I have Thursday first hour and Friday second hour for network analysis, so both the classes I'll be taking. I'll see, depending on how much material is needed to be covered, I will either record a video and then post it, and or I think probably I'll do that, and one more class I'll take in analog, one more class in networks. Okay. All right. So I have already
Sir, I have
put
a
the
doubt.
yeah.
Sir, when we are adding VB, like we are getting V in P and V in M, we are losing the DC component of the signal, right?
Yeah.
So
Yeah,
how can we need that also, right?
Not necessary. So typically the DC component is mainly to bias the whole thing. All right. And usually when you talk about any signal, let's say you talk about biomedical signals, or if you're talking about audio or whatever it is, you're mostly looking at the AC signal. It's only in very few cases you are looking at DC signals by themselves. And so here also, if you have let's say a DC input, okay, let's say that delta V is a DC, again you will have a DC output where V out 1 is not equal to V out 2, right? So this works for DC signals also.
So but here we are again having two outputs, like we are not having the difference output.
Yeah, so there are ways to convert, there are ways to convert a differential signal to a single ended signal. I thought that was a little beyond the scope of, if you can look at this particular thing, I thought I try to discuss this in today's class, but of course we didn't have the time to do that. So this is a simple op amp, okay. Of course, this is not completely a full op amp. Not all the things are shown. You can see that the current source is, this is your differential pair. Okay, this node 1 and node 2 are the two plus and minus terminals of your op amp. Okay, Q1 and Q2 are the differential pair. The current source is implemented by Q3. Okay, and the bias is coming from a current mirror. Okay, I mentioned about current mirror. So this is the current source. You have 20K, 20K. Two inputs are going to the next stage. So this is a multi-stage differential amplifier. Okay. In the second stage, Q4 and Q5 form the second stage. I took this from Cedar Smith. You'll find it in the textbook. You can go through the analysis of this one. Right. So here Q4 and Q5 form the second differential pair. Okay. And here, it is 4 times the current. Okay, Q6 is 4 times the size of Q9, and therefore you'll have 4 times the current. You can see this is 0.25 and this is 2 milliamp. Now what happens is, you are connecting the resistor only on one side, and as we know that the current kind of circulates inside. Okay, so if you take the output from only one side, that basically has the differential information. And of course there are more elegant ways to get it done, which we have which is not shown here. You can put a current mirror load here and take it, and then here this is the third stage, this PMOS Q7 and this resistor. This is a common emitter amplifier again with degeneration, right? So, and then Q8 and 3K resistor is the common collector stage, okay, which is to provide the output drive. So this is the way. This is one way to convert differential to common mode signals. Okay.
So we could just use the differential amplifier. I mean, we could use the difference op amp circuit, right?
Right. You can use. What we are talking about here is the internal structure of an op amp. Okay. This is a very crude, let's say, op amp. This is not a full-fledged op amp. A full-fledged op amp like 741 or OP01 or 07 will have a little more complicated circuitry, but this is like a very elementary design of an op amp. Okay. So there are other ways, like you can put a current mirror load. So probably I don't know if I downloaded the data sheet. I can, let me just see quickly if I have the right. Okay, I haven't downloaded that, unfortunately. Okay, I thought I downloaded it somewhere. Okay, anyway, so let me, maybe when I create a video, I'll just show that how it is working. Okay. The other thing is, I have already talked about, I have already put all the instruction about the lab exam tomorrow and day after. One more piece of information is that because triple timers have not been taken for you, I had a discussion with Dr. Anup. So for the lab also, we will skip the 555 timer based experiments. Okay. So the op amp based astable multivibrator, you can do it with just the op amp. And more, what I would do is, instead of the 555 version, we will have the monostable multivibrator design for today using op amp. So the 555 timer will be taken, he said, in the instrumentation course, and you will learn it there. So we will not have that. Yeah.
Did it in last lab.
Sorry.
We already did it in last lab.
555 timer.
Yes,
sir.
Okay. So you guys went through the 555 timer, understood how it is working, or it was just blindly take the circuit?
No, sir. Blindly we just took that circuit.
Okay. No. So in that case, we will not include it for the lab exam. If you have done it, that's fine, but I'll not include it in the lab exam, because if you haven't understood how a 555 is working, then there's no point in going through that whole thing.
So what about the oscillator, Weinbridge oscillator and silent key?
Yeah, so Weinbridge as a silent key, again, I think you have not learned, so we will avoid the silent key experiment as well. Okay. Instead, what we will do is Weinbridge oscillator, I think, has already been taught, right?
No, sir.
started with oscillators.
Okay, so
Anup
you
sir
have
might
it
take it tomorrow.
probably. Okay.
So we're going through a lot, sir, right now.
Yeah, I understand. I think all the faculty will be kind of loading you with a lot of classes and
Sir, not
information.
even loading, sir. Sir, they're
At
like
least our
writing.
assignments, classes, and internals.
Super loaded, sir. Super
Yes,
loaded.
sir.
Reports, lab project.
Okay. Yeah,
Sir, I
Sir,
think
can we submit lab reports after NSEM, like 2 or 3 days, like 19th or 20th? Like, can we have that deadline for all the lab reports?
uh, actually, your
Either
lab
they'll be
reports, I
complete.
don't require you to write much. See, the whole point, one of the main motivations for making you do the lab report is such so that you will have it for a reference when you are preparing for your lab exam. Okay. In fact,
But
like last,
we are
yeah.
not done, sir. So
20 marks
can
are
we
there,
have?
sir.
Sir, we have not learned it.
Okay.
So
So
20
like
marks are assigned for lab report. So we have to
right.
submit all anyway.
Correct. So that is to evaluate whether you have been following the lab sessions properly and in fact I think last year I didn't even have a component for that lab reports because anyway their physical attendance was taken and yeah, I mean that was there, so I didn't have any component for lab report. Now that it is online, I don't know how many are actually taking part in the lab and how many are not doing anything. So that is one reason why I had this. See, you can avoid, you don't need to sit and type out anything. When you're doing the lab thing, just write it in sheets of paper, take a photograph, make it a PDF and upload. That is enough. Okay. There's no joke in doing your lab reports after the lab's exam is over. One of the main motivations is that you
So
know
what
how
all
to
are you supposed to like the circuit, the like manual calculation?
see. Just write first of all the specifications given, right? That is already given to you, and
Yes,
draw the circuit diagram freehand. No need to do it in any circuit software or anything. Okay, and then what you do is you write your design procedure, whatever you are anyway doing in the lab session, right? The calculations that you do for whatever components you are calculating, just write them in sheets of paper. Even if it is messy, where you're just striking out things and writing, that is fine. That's how a lab report is supposed to be. Okay, a lab report should not be. I mean, if you're really doing an experiment, of course, now you're virtually doing, that is a disadvantage. But if you're really doing an experiment in lab, it should be dirty. Okay, so whatever calculations you're doing, mistakes you're doing, it's fine. You can strike out right things. Okay, and then the final values. Okay, and then the measured results. Okay, for each experiment you'll be measuring different things, right? And then the graph that you're plotting. Okay, just put all these things together, take photographs and put them together as PDF and then upload them. That is enough. And that is what you need to do even for tomorrow and day after's lab exam, right? So you have to write your calculation. So again, let me give you the instruction here itself, right? You need to you will be given a question. So you have to do your calculations and give the final component values, your simulation results, because right now you're not. So for the lab report, you don't need to do simulation, but for the final exam, you have to do simulation. So if you want to kind of brush up things like how to include an op amp in LT spice, how to include BJT, which BJT you are including, what are the parameters for BJT. So all those things. So how are you simulating in LT spice for BJT? Are you taking an existing BJT?
So
So
we are
like
taking the value from the lab.
Sorry?
Sir, actually, some of us are doing by using the beta values of the lab and using a standard NPN transistor.
Okay.
But some of us are downloading the model of BC107 and then changing the beta value.
Okay. So what you can do is for all transistor related experiments, you can just take the beta to be 200 for tomorrow and I mean for the lab exam. Okay. So whether you include the what about IS? IS you're okay. Let me just dig up a little bit and I'll in case you need to enter parameters, I'll just give you the parameters. Okay. And so what are the parameters you are entering for BJT if you are taking from the data sheet?
Entering IS and junction potential and the beta value. These three we are entering mainly, sir.
Sometimes
Okay.
early voltage
And
too.
sometimes early voltage also.
Okay. Yeah. So these. So what is the early voltage that you are using?
100 or 200.
150 and
Okay.
sometimes 200.
Okay. So I will give you the values for whatever you are simulating. Op amp, how are you using? I think op amps, LT Spice will have plenty of op amps, right?
Yes.
Yes, sir.
Yes,
Yeah.
sir.
You can take any one of them and simulate. Okay. So just make sure that you are able to simulate and prepare for that. And because anyway, there is no. I actually thought we can get it done with the lab stuff, but then it's extremely, putting a lot of pressure on the lab stuff. That is too much pressure. So let's just do a simulation exercise. All right. And yeah.
Sir,
So
and
that's the thing.
So one
sir,
doubt.
when we simulated the multivibrator, a stable multivibrator in Spice,
Okay.
so like even if I design for 7.5 kilohertz, I'm
Okay.
getting a maximum frequency of only 6 kilohertz.
Yes,
So
sir.
why is
It
that,
was
sir?
never coming 7.5 kilohertz. Even like many designs we tried by the theory.
Sir,
Mhm.
and in the lab we did 1 kilohertz. So I just
Mhm.
reported 1 kilohertz one. That is working out fine. That is coming out nearly 940 hertz. That is fine.
Mm-hmm.
For 7.5 kilohertz, they're having a appreciable drop in the
Okay. Have you
frequency.
tried the 7.5 kilohertz in lab?
No, sir. Actually, I didn't see the Moodle page then. So,
Okay.
uh,
Okay.
yeah,
Okay.
in detail I didn't see. So I just thought that we have to design for 1 kilohertz. Even I asked the madam, she told 1 kilohertz will be fine. So
Okay.
then
Okay.
we designed and I submitted. Then
Hmm.
after the lab, I designed for 7.5 kilos and tried simulating, but it is not happening. Even many of
Which op amp?
others are, sir.
Which op amp?
Sir, LM741.
741 is it?
Sir, even I tried it using OP07 and mu A741, but it's not working. All the same, similar results only.
Mm-hmm. So one
Tried in
thing. So are you getting some kind of a triangle wave?
Yes, sir.
Yes, sir.
Okay. So the op amp is slewing basically. So that's the problem. Okay. Then
So, no, sir, in the
let
triangle wave generator, we are getting
no,
triangle wave.
not the triangle wave generator, but like when you're trying to simulate a square wave, are you ending up instead of a square wave, are you getting a triangle wave?
No, sir.
Yes,
Yes,
Trapezium.
Something
yes, sir.
There
Yes,
is
sir.
a
yes, sir. It
there is
is
a
getting
slight
triangulated.
slope. There is a slight slope in the transition when we
Yes,
observe the slope.
Like
that
said,
is
the T
significant, sir.
fall and T rise is very like more comparable to the T
So like
time
for
period.
higher voltages, it's coming like triangle wave, but for
Hmm.
smaller voltages, it's coming like
Yeah, basically that is the slew rate,
somewhat like
slewing. The op amp is slewing. It is unable to handle that slew. Basically, that's the problem. Okay, you
For
have already.
universal op
Yeah.
it was coming out to be correct.
Which one?
There's
Can
an
you repeat
option
that?
in LT Spice universal op amp.
Okay.
For that, the output was coming out to be correct.
Yeah, yeah. That is because like the slew is not included in the simulation.
Mm.
Yeah, this is basically slew rate limited. So maybe I'll just restrict the questions to less than 5 kilohertz. Yeah.
Sir, and one more, sir, while simulating for 7.5 kilohertz,
Okay.
I mean, like, sir, square,
Sriram, your voice is
this
breaking.
output is getting
I don't know if my connection is bad or yeah. Can you repeat, please?
Sir, his voice is breaking.
second.
Oh, his voice is breaking. Yeah. Yeah.
Yes, sir. Am I audible now?
Yeah. Yeah. Now it's better.
So I was saying the resistor in between the two stages, that is like that we use for the integrator one, that coming out from V out one and going into the second op amp. So like I try to keep it considerably low, like something like some hundreds of ohms, so that I'll get output amplitude close to the like with amplitude almost same as the square wave amplitude. So, but I think because of the short circuit current, like it's getting kind of
Yeah.
like a
Yeah.
sine wave current and all that.
Right. Yeah. See, the amplitude is okay. Even if you get a smaller amplitude, that's still fine. Okay, if you can generate the the circuit, that is enough. I mean, if you generate the waveform, that is enough. Yeah, I think Santosh has asked what to do if we haven't learned any of the two. Okay, so let's leave the Salenki filter. Okay, the filter. Let's leave the 555 timer based circuits. If you haven't done, leave it. If you have done it already, it's okay. You don't need to submit a report for it, because if you don't understand how it is working, no point in doing it. Okay. And what else did I give today? Uh, I think it was that triangle wave generation, right?
That we have done.
Bridge.
That we have done, sir. Wein
Okay,
bridge also.
Vein
Vein
bridge
bridge
also,
also you have not done, right?
yes, sir.
Okay. All right. So then maybe let's leave that as well, because I think Dr. Aunap might teach that tomorrow, but it's kind of too much to expect you to, try to learn that and do it. Okay. What do you guys want to do? I mean, the equations are
So
simple. The frequency is 1 by RC, 1 by 2 pi RC, and you have a negative feedback network which sets the
Sir,
gain, and the positive feedback network which sets the frequency.
So we have done this in the ECAD lab. So,
Okay.
but designing portion is like kind of tricky.
Right. Okay, let's leave it. Let's leave it, because I know, I mean, with all this lockdown and other things already, a lot of issues faced. So let's leave that as well. Then today's lab, whatever you haven't done so far, you can do it. And you know, if you want to repeat any experiment, you can do so. Okay, and you can try to simulate each of these things um, in LT-Spice and then see. Okay. So that's the way we will have our lab session today. Weinbridge is out, and filter is also out. Maybe what you can do is you can design a simple RC filter, active RC filter, but again, that's too simple for you to do. So we will
Sir, can we
probably,
repeat the common emitter plus common collector
yes,
phase
you can repeat. So
amplifier? Because
probably,
that
mm,
in that we were not getting the correct.
right. So you can repeat those experiments. Okay, whichever experiment you want to repeat, you can repeat. You can go through all the experiments, try to simulate them, uh, and this thing. Okay, Sriram has another question. Current source circuit, you're getting lower output current for higher load resistance in SPICE. Uh, you can expect that, because for as the high load impedance increases, the voltage across the load also increases, which means it kind of starts crunching your PNP transistor that you have put. Okay, you have a resistor and a PNP or an NPN transistor, right? And so that can basically come and really hurt you. So that is to be expected.
Solution? What is the solution like?
That is the limit.
Uh,
Nothing can be done.
We can increase the supply voltage for
Supply
them.
voltage you can increase if the op amp supports it. And
Okay, sir.
more than the op amp, I mean, the op amp can take plus minus 15, which means 0 to 30 also it can support. But what about the transistor? The transistor will not be able to handle very high voltages. Okay, so that's the thing.
Yes, sir.
Yeah. So Murtaza, the reports to be submitted. What did I give in Moodle? What I can do is I can extend the deadline till Friday. Okay.
Yes, sir.
I'll extend the deadline to Friday. Okay, you guys prepare for your exam. I thought the reports will be useful for your exam. That was what I thought. Okay. And yeah, Siddharth has a question which is like, you can use non-standard values of resistors, but I would prefer that you use the standard values. Okay. In fact, for one or two of the assignments, I've given the standard resistor sheet. I would prefer that you use the standard ones. Okay. Saurav is asking, can you use universal op amp for exam? No. Please try to use either OP07 or 741 or any of the other real op amps. Okay. So don't worry, I'll not give you 7.5 kilohertz. I'll try to give you lower values. Okay.
Sir, and one more thing. While
Yeah.
designing the capacitances, like should we take it arbitrary or should we keep in mind the frequency response and all the stuff?
You can design it with the frequency response, but it's a little,
Time consuming.
complicated, like, yeah, and time consuming. So last time I asked the students to do that. I mean, so the same equation that we developed today, right, for multiple poles, you kind of have to use that and, look at those things. But I think it's okay. Just take some fairly large values such that, it is it's able to handle low frequencies. Yeah. Okay. All right. So today you can repeat whatever experiment you want, and I'm just thinking, instead of the silent key filter, would you like to implement a active RC filter, a normal first order active RC filter, which you have learned?
Yes, sir.
Okay, maybe then you can take the same question. What
So
was
we
it that
can
I had given?
maybe, so maybe you can do the 20 one.
You can maybe, yeah, you can have a gain of, let's say, 10 and a corner frequency of, let's say, 5 kilohertz. Okay. You can basically use a non-inverting, an inverting amplifier, and put a capacitor in parallel. It's a very simple thing, but you need to plot the frequency response. Okay. So gain of 20, gain of what did I say? 20 or 10? 10, right? You can have a gain of 10 volt per volt at low frequency and have a corner frequency of 5 kilohertz. Do it with a simple active RC filter. You can do it in multiple ways, like whichever way you're comfortable with, you can do. Okay. All right. You can use the non-inverting configuration. You can use the inverting configuration. Both are fine. Okay. So let's conclude today's class. And yeah, thanks.
Thank you, sir.